Witness the awe-inspiring installation of massive machines and towering cranes, where engineering brilliance meets sheer power on epic construction sites. The assembly of the Grove GHC130 crawler crane follows a fully self-rigging sequence that allows the crane to be prepared quickly and without the need for large amounts of auxiliary equipment. The procedure begins when the crane is positioned at the worksite and supported by frame-mounted hydraulic jacks. These jacks provide the necessary stability during unloading and initial setup. With their two-position design, the jacks can be adjusted to suit different trailer heights, which simplifies the transition from transport mode to assembly mode. Once the crane is securely raised, attention shifts to the tracks. The track side frames are placed in the dedicated holders alongside the car body frame. Hydraulic clamping mechanisms are then activated to secure each track firmly to the car body. After physical installation, hydraulic connections are attached. These quick connections supply fluid to the two-stage traction motors integrated in the track frames, ensuring the crawler system is immediately operational once the crane is lowered onto its tracks. During this phase, the operator uses a wireless remote control to maneuver the crane while it remains supported on the hydraulic jacks. This remote system provides accurate control and mobility, which is essential for positioning the tracks and for the next major stage of assembly, counterweight installation. The counterweight system is entirely self-assembled. First, a base plate equipped with lifting lugs is positioned on the rear of the crane. This base plate serves as the foundation for the remaining counterweight slabs. Using counterweight lifting cylinders and chains that are pinned to the base plate, the crane raises and positions each slab sequentially. 4 interchangeable slabs are added in this way, creating the full counterweight package. The use of integrated cylinders eliminates reliance on external lifting equipment, streamlining the process considerably. The assembly of the Mammoet CC680 crawler crane begins with careful site preparation and mobilization. Heavy transport vehicles deliver the crane's major components, including the base crawler tracks, central superstructure, counterweights, boom sections, and luffing jib parts. Each element is positioned in sequence to facilitate efficient assembly. First, the massive crawler tracks are unloaded and aligned on prepared ground. Hydraulic systems and jacking equipment stabilize the track frames, forming the base on which the crane will stand. Next, the central superstructure is lifted into place using auxiliary cranes. This superstructure houses the slewing ring, machinery deck, and operator cab, and it connects the tracks to the upper crane elements. Following this, the main boom assembly begins. Individual lattice boom sections, fabricated from high-strength steel, are pinned together horizontally on the ground to form the 66-meter boom length specified for the project. Once connected, the boom is carefully raised with the help of assist cranes and secured to the superstructure's boom foot. Hydraulic and mechanical pins are locked to ensure rigidity. The 84-meter luffing jib, a crucial extension for reaching greater heights, is then assembled. Similar to the main boom, its sections are joined at ground level before being lifted into position. The jib is attached to the main boom head and connected via pendant lines, allowing precise control of angles during lifting operations. Counterweights, critical for crane stability, are installed on the rear of the superstructure. These massive slabs of steel are carefully placed using assist cranes and secured to balance the crane's enormous lifting capacity of up to 250 tons. Finally, all mechanical, hydraulic, and electronic systems are tested. This includes calibrating the control system, verifying wireless communication, and ensuring safety interlocks function correctly. Once assembly is complete, Mammoet's team performs a thorough inspection to certify readiness. The fully assembled Mammoet CC680, with its 66-meter boom and 84-meter luffer, is then prepared for operation, capable of executing heavy lifts for large-scale industrial, infrastructure, or plant projects with precision and safety. The assembly of Tut Bryant's new Demag CC8800-1, the largest crawler crane in Australia, begins with the installation of the massive track units. These heavy-duty tracks are positioned and secured first, forming the foundation for the crane's mobility and stability. Once the tracks are in place, the cross beams are attached to provide structural support and link the undercarriage components together. Following this, the central section with the large slew ring is mounted. This crucial component allows the crane's superstructure to rotate smoothly during operation. With the base structure complete, the connectors to connecting additional support frames and hydraulic systems. Finally, the enormous main boom and crane attachments are carefully installed, completing the build. Each stage of the process is carried out with precision, ensuring the CC8800-1 is ready for its demanding lifting projects across Australia. The installation of the tower crane at the Tut Bryant Hospital construction site demonstrates a carefully planned and sequential process, ensuring both safety and efficiency for the demanding tasks ahead. After the foundation and base section were securely prepared, the focus shifted to erecting the tower itself. The procedure began with the delivery of prefabricated tower sections to the site. Each steel section was lifted into position by a mobile crane and carefully aligned before being bolted together. The first few sections were erected directly onto the base, providing a stable foundation for the rising structure. As each segment was positioned, workers used high-strength bolts and torque tools to secure the connections, ensuring rigidity against wind and vertical loads. Once the initial sections reached a sufficient height, the process of installing the slewing unit and operator's cabin commenced. The slewing ring, which allows the crane to rotate, was carefully hoisted and fitted on top of the tower. Immediately after, the operator's cab and electrical systems were installed, giving the crane its functional control center. This stage required precise coordination, as the cab integrates directly with both the slewing mechanism and the future jib system. Attention then turned to assembling the jib, or horizontal working arm. First, the counter-jib was installed, carrying ballast weights and housing the winch system. This counterbalance is essential to offset the load carried by the main jib. The counter-jib was lifted and pinned into place, followed by the gradual installation of the main jib sections. Each segment was raised and attached in sequence until the full span of the jib was achieved. During this stage, tensioning of the tie rods was performed, ensuring that the horizontal arm maintained proper alignment and load-bearing capacity. With the main structural components in place, the hoisting system was completed. The trolley, which travels along the jib, was mounted and connected to the hoist rope system. The winch drum and pulleys on the counter-jib provided the driving force, allowing loads to be lifted and moved horizontally. Electrical connections and control systems were then tested, ensuring the crane's operational readiness. A critical part of the installation involved the climbing mechanism. Since the hospital project required considerable building height, the tower crane was designed to grow along with the structure. A climbing frame, installed just below the slewing unit, allowed new tower sections to be inserted. By using hydraulic jacks, the slewing unit was lifted slightly, creating space for workers to insert and bolt an additional mast section. This climbing procedure could be repeated whenever greater height was required, allowing the crane to rise progressively as the hospital's floors were constructed. Final adjustments were made to verify vertical alignment using surveying instruments. The crane's stability, braking systems, and limit switches were also checked thoroughly before being handed over for construction use. Through this step-by-step assembly, the tower crane at Tan Nam Hospital was successfully erected, becoming the central piece of equipment to lift heavy materials, facilitate structural work, and support the timely progress of the entire project. At Gamuda Garden in Rawang, an advanced beam launching method was applied to position large precast beams with remarkable precision. The process relied on a specially designed launching girder, capable of handling the size and weight of the beams involved. Each concrete beam measured 63 meters in length and weighed approximately 114 tons, demanding a robust and carefully coordinated installation system. Hi-ho. The launching girder was first assembled and aligned with the span where the beam was to be placed. Its structure served both as a support and a guide, ensuring that the heavy beams could be moved safely into position without the need for conventional ground-based cranes. Once the girder was properly anchored, the precast beam was lifted onto the system and gradually pushed forward across the span. Hydraulic mechanisms and rollers enabled smooth and controlled movement, reducing the risk of damage or instability during placement. This method proved highly efficient for bridge construction in tight working areas, as it minimized ground obstruction and enhanced safety. By using a launching girder, the project team at Gamuda Gardens successfully placed massive 63-meter beams with precision, speed, and reduced environmental impact. The erection of pre-stressed concrete eye girders is a critical stage in the construction of modern highway bridges, requiring precise coordination, powerful lifting equipment, and strict adherence to safety standards. At the Trans-Sumatra Toll Road project, a PCI girder measuring 40.8 meters in length was installed using a dual-crane lifting method. This operation highlights both the complexity and the efficiency of handling long-span bridge elements. To begin, the PCI girder was delivered to the construction site by a specialized transport vehicle. The girder, due to its considerable size and weight, cannot be installed using a single crane alone. Instead, two crawler cranes with adequate lifting capacities, one rated at 180 tons and the other at 250 tons, were employed. This combination ensured both the strength and the balance needed to safely maneuver the girder from the transport vehicle to its final position. Bassiasis. The lifting process commenced with the careful attachment of rigging and slings to the designated lifting points of the girder. Each crane was aligned along the span, one operating at the front end and the other at the rear end of the girder. Synchronization between the two crane operators was vital, as any imbalance could cause the girder to twist, leading to structural damage or safety risks. Once the rigging was confirmed secure, both cranes gradually took the load, lifting the girder steadily off the transport trailer. As the girder was raised, spotters and supervisors guided the cranes to rotate and shift the load toward the bridge alignment. This stage demanded meticulous control, with both cranes maintaining equal tension and height to avoid uneven stress distribution. The suspended girder was then slowly swung over the pier and abutment area where bearing pads had already been installed. The erection phase required careful maneuvering to place the girder directly above its supports. Workers stationed on the pier provided hand signals and radio communication to guide the operators with precision. The girder was then lowered onto the bearings in a controlled manner. Once contact was made, minor adjustments were performed to align the girder with the exact coordinates specified in the construction drawings. This included fine-tuning its longitudinal position, transverse placement, and rotational orientation to ensure a perfect fit. After the girder was set on its bearings, temporary supports and safety clamps were used to stabilize it until additional girders were installed alongside. The erection team then inspected the alignment, confirming that the girder matched the project's engineering tolerances. This verification step is crucial, as any misalignment at this stage could affect the continuity of the superstructure and the subsequent deck installation. In conclusion, the erection of the 40.8-meter PCI girder at the Trans-Sumatra Toll Road project demonstrates the complexity of bridge construction involving long spans. Using two crawler cranes with capacities of 180 and 250 tons provided the necessary lifting strength and stability, while precise coordination ensured safety and accuracy. Through careful lifting, positioning, and alignment, the girder was successfully installed, marking a significant milestone in the advancement of the project's bridge structure. The installation process of the SANY SCC6500A 650-ton crawler crane starts with setting the upper and lower carriages into position. The slewing bearing pins are carefully inserted to connect these two key structures, forming the base of the crane. Immediately after, anti-loosening clamp plates are mounted onto the slewing pins to ensure they remain firmly locked in place, preventing any unwanted movement during subsequent operations. With the carriages secured, attention turns to the luffing mast. This component is assembled and attached to the crane's main body. At this stage, the rear backpack section is separated to allow proper configuration for later assembly steps. Utilizing the one-key luffing function, the mast is slowly raised. The mast angle is carefully adjusted to exceed 95 degrees for correct alignment. However, during actual lifting work, the ideal operating angle is maintained between 65 and 75 degrees. Once the mast is in position, steel wire rope slings are attached to prepare for lifting the heavy crawler assemblies. Next comes the installation of the crawlers. Each crawler track is hoisted with the help of the slings and guided into place alongside the undercarriage. After precise alignment, hydraulic insertion pins are engaged to secure the crawlers to the base structure. The support leg cylinders of the lower carriage are then retracted, allowing the full weight of the machine to transfer onto the newly installed crawlers. Hydraulic hoses are connected to the crawlers, enabling full mobility and stability on the ground. The assembly then proceeds with the installation of the central configuration platform. This includes mounting the counterweight tray, working platforms, and access walkways. Following this, the superlift mast boom sections are prepared. These sections are aligned and joined together with hydraulic pin pushers, ensuring strong and accurate connections. Once completed, the superlift mast assembly is installed onto the crane's body, again locked in place using hydraulic pins. Rope reeving operations are carried out on the mast, preparing it for heavy-duty lifting. The rear counterweight tray is then mounted onto the structure, adding the required stability. With this support in place, the superlift mast is raised into its working position. At this point, the main boom tie plates are installed, providing a strong link between the mast and the main boom. Electrical cables of the boom are also connected to the appropriate plugs to ensure communication with the crane's control systems. The main boom itself is now installed. It is carefully lifted into place and locked securely with hydraulic pins. Rope reeving is extended through the main boom, completing the hoisting path. Following this, the hydraulic hoses for the superlift counterweight are connected, and the counterweight tie plates are secured. Boom guy ropes are then added, providing further bracing and structural integrity during heavy lifting tasks. In the final stage, the main hook is mounted onto the reeved hoist line. With all assemblies complete, the boom is slowly raised into its working angle, supported by the counterweights and reinforced by the mast and tie ropes. At this point, the SANY SCC6500A crawler crane stands fully installed, with every major component, including the mast, boom, counterweights, and hook system securely in place, ready for heavy lifting on site. The Liebherr LR13000, the most powerful conventional crawler crane in the world, was employed by Mammoet for a remarkable lifting operation in Bremerhaven, Germany. In this project, the crane was tasked with installing 4 massive platform legs on the wind turbine installation vessel Aeolus. Each of these legs measured 87 meters in length and weighed an impressive 920 tons, presenting an extraordinary challenge in terms of both size and precision. Aeolus itself is a highly specialized vessel, designed specifically for offshore wind power installation. With a length of 139 meters and a breadth of 38 meters, it provides the necessary stability and capacity for transporting and positioning heavy wind turbine components. However, before the vessel could be deployed for its offshore mission, it required the installation of its enormous legs, which enable it to stand firmly on the seabed during wind turbine erection at sea. To handle such extreme lifting requirements, the LR13000 was equipped with the power boom system. This configuration significantly increases both stability and lifting capacity, allowing the crane to safely manage loads of this magnitude. For the Aeolus operation, the LR13000 was configured with a total boom length of 132 meters, enabling it to reach the necessary height and radius to position the legs precisely onto the vessel structure. The lifting sequence involved carefully maneuvering each leg into position, rotating and aligning them with millimeter-level accuracy before lowering them into their designated slots. The entire operation demonstrated the synergy between advanced engineering, careful planning, and the extraordinary capability of the LR13000. By successfully installing the 4 massive legs, Mammoet and Liebherr ensured that Aeolus was fully equipped to embark on its mission of building offshore wind farms, contributing to the expansion of renewable energy infrastructure. The installation of an offshore oil platform is a highly complex operation that demands precision, heavy equipment, and seamless coordination between vessels and crews. The process begins with the planning and execution oversight of a team often referred to as the Brains Trust. This group of engineers, supervisors, and safety experts carefully monitor each step to ensure that every activity is executed safely and according to schedule. Their decisions guide the OV. At the heart of the logistics lies the material barge. This massive vessel carries the critical structures and equipment required for the platform assembly. It transports the steel jacket, piles, topside modules, and auxiliary components from the fabrication yard to the offshore installation site. The barge provides a floating workspace where heavy lifts can be prepared, and where welders, riggers, and constructed.io. The first structural component to be installed is the jacket. This is the enormous steel lattice framework that will serve as the foundation of the offshore platform. Once positioned alongside the installation site, heavy lift cranes carefully conduct the jacket lift. The operation involves hoisting the jacket from the barge and lowering it precisely onto the seabed. Correct positioning is essential as the jacket must align with predetermined. With the jacket in place, the next step involves securing it to the seabed using the piles. These long, tubular steel elements are driven through the jacket legs into the seabed to anchor the structure. Before they are fully embedded, teams carry out welding the piles, attaching them to the jacket legs and preparing them for permanent fixation. Once welding is complete, heavy pile-driving hammers are used in the stage known as hammering the piles. This activity forces the piles deep into the seabed until As the platform requires multiple anchors, the process is repeated with more piles being lowered, welded, and positioned. Each pile undergoes another sequence of more hammering the piles, ensuring that all legs of the jacket are equally secured and that the foundation can withstand environmental forces such as waves, wind, and currents. Once the piles reach the target depth, excess steel sections protruding above the jacket are removed during the pile cutoff stage. This ensures a smooth TRA. To further stabilize and align the jacket, the crown shims are installed. These precision components fill the gap between the top of the piles and the inside of the jacket legs, creating a tight and secure fit. The shims prevent movement, distribute loads evenly, and guarantee the long-term stability of the foundation. Following this, the crews proceed with constructing the boat landing. This vital feature allows supply boats and crew transfer vessels to safely dock and deliver personnel, equipment, and provisions to the platform. With the foundation secured, attention shifts to installing the topsides. These massive modules contain the drilling rigs, processing equipment, living quarters, and control systems necessary for platform operations. Using heavy lift vessels, the topsides are carefully hoisted and aligned onto the jacket legs. Precision is critical during this phase, as the modules must fit seamlessly with pre-installed connectors and support structures. The successful placement of the topsides effectively transforms the bare steel foundation into a functional offshore production facility. Finally, the process concludes with completions. This stage includes all finishing activities, such as connecting electrical and control systems, commissioning pipelines, and testing safety equipment. Crews carry out final inspections to ensure that every weld, joint, and component meets rigorous offshore standards. Once completions are verified, the platform is fully operational, ready to begin drilling and production activities. Overall, the installation of an offshore oil platform is a remarkable demonstration of engineering and teamwork. From the careful oversight of the brains trust, through the precise placement of the jacket and piles, to the final completion of the topsides, each phase builds on the previous one with meticulous attention to safety and accuracy. The end result is a robust structure capable of withstanding harsh marine environments while enabling the exploration and extraction of vital energy resources.